Hey everyone, Victor is here, and in this video I want to talk about the ether cleavage. We've already seen how we can make ethers via the Williamson ether synthesis, and if you haven't seen that video yet, I'll leave the link in the description below. Now, let's talk about how we break them. So grab your cup of coffee and notebook to work through the examples with me, hit that like button for good luck on the test, and let's get started. There are several ways how we can cleave our ethers. In this tutorial, I'll focus on the most common one, reaction with hydrogen halides such as HI, HBr, and HCl. And you might have already guessed, it's going to be either an SN1 or SN2 reaction depending on the structure of our ether. So to start things off, let's look at this reaction of the diethyl ether with, let's say, something like HBr. Since HBr is a pretty strong acid, the first step is going to be the proton transfer, in which we're going to be protonating the oxygen of our ether. This creates a leaving group, and we can consider either side of the molecule as a leaving group in this case, so it doesn't matter. Importantly, since this would be a primary leaving group, the SN1 pathway here is simply impossible despite the project conditions. This means that we'll have to attack the carbon directly via the SN2 pathway. This gives us an alcohol and alkyl halide, but since the reaction is typically done in the excess of HX as an acid, those are not going to be our final products. In the next round of this reaction, the HBr going to attack our alcohol, making H2O leaving group. In this case, just like in the previous round, we cannot form a carbocation as it would be too unstable, so we'll have another SN2 attack by the halide. As a result, we're going to get another equivalent of our halide product. In this case, since the molecule is symmetrical, we get bromobutane as our product. However, if molecule is not symmetrical, you'll get two different alkyl halides. For instance, if I treat this butyl ether with, let's say, something like HBr, then in this case one product will be the bromoethane, just like in the previous example, and the other product will be 1-bromobutane. And of course, we'll have water as our co-product, but as in the case with any inorganic co-products, we don't really care about it. Now, moving on to the more complex molecules, what if we have a tertiary or secondary ether? Well, in this case, we're going to go through the SN1 mechanism. For instance, if I have this ditert-butyl ether and let's say I treat that with something like HI, then in this case, we're going to end up with two equivalents of tert-butyl iodide, or if you prefer the IUPAC name, it's going to be 2-iodo-2-methylpropane. From the mechanistic perspective, this reaction will start the same way as the last one. We'll first protonate the oxygen, making a leaving group, and like in any case with the ether cleavage, it is going to be irrelevant which side you're going to treat as your leaving group here, so go with whichever you like or hate the most, I guess. So once we have our leaving group, the dissociation here won't be an issue because the tertiary carbocations are relatively stable and they can form comparatively easily. And lastly, we'll have the nucleophilic attack on our carbocation that going to give us the first equivalent of our alkyl halide. Of course, that's not going to be the end. We are going to go into the second round of this reaction by protonating our alcohol, which going to end up giving us water as the leaving group, and once that leaving group dissociates, we are going to end up making a corresponding carbocation, and then of course we're going to have another nucleophilic attack by our iodide, giving us the second equivalent of our alkyl halide product. Naturally, if you have a mixed ether, like for instance in this case we have a sec-butyl isopropyl ether, you are going to make two different alkyl halides. But do you really want to go through the mechanism every single time? Well, probably not. Going through the mechanism for every reaction on the test is really tedious. You still want to make sure that you do know your mechanism though, so don't just rely on the trick that I'm going to show you every single time. But nonetheless, your instructor will also expect you to be able to predict the product fast without having to draw the mechanism for each single reaction on the test. Well, luckily for us, predicting the products in the ether cleavage is actually quite easy. First of all, we are going to redraw our ether, leaving some space around the oxygen. Then we are going to erase that oxygen, and finally we are going to add halides to the bonds that used to be connected to the oxygen, and we are done. Easy peasy. Now, being an organic chemist means that I, at least according to some of my students, hate fun. And while I strongly disagree with this statement, I do have to admit that we, organic chemists, like to throw a curved ball at our students from time to time on the test. So here are a few common mean questions that you might see on the test. First, I'll start with something more innocent. Cleavage of a cyclic ether. Remember that if we are cutting through a cyclic molecule and we're only doing so at one location, we're not going to be making two different products, rather we are going to end up with one long chain. So, for instance, in this case, if I look at this reaction of the tetrahydrofurane with HBr, then in this case, we're going to quickly go through the mechanism. Actually, I'm not going to go through every single step, but if you need a little time to follow through the steps here, make sure you pause this video and study those steps carefully so you can write similar mechanism on the test if you need to. But the point here is that when you are doing reaction like that, instead of making multiple products, you are actually going to end up with one long chain of a product. Here is another common tricky question that instructors love to throw at students on the test, and that is the cleavage of phenyl ethers. So for instance, here I have phenyl propyl ether, and let's say I'm going to treat it with something like HI. Well, in this case, the right side of the molecule will turn into corresponding alkyl halide, 1-iodopropane, nothing unexpected in this case. However, the left side of the molecule with the phenyl group will stay with the OH. Remember how you cannot easily do a substitution on the sp2 hybridized atoms? This is the case here as well. Phenol, my other product here in this reaction, has its OH group that is sitting on the sp2 hybridized carbon, and because of that it cannot be replaced with iodine via either SN2 or SN1 reaction, so it stays as is. Finally, if we have secondary ethers, there can be a possibility of a carbocation rearrangements. So for instance, in this molecule, I have my oxygen attached to the secondary carbon, which is going to be right next to a tertiary position. So if I were to treat this ether with something like, let's say, HBr, I would end up with the secondary carbocation in the middle of my mechanism. And since secondary carbocation is right next to a tertiary position, I would immediately see the carbocation rearrangements, giving me a more stable carbocation. Remember, if a carbocation can rearrange to give you a more stable carbocation, it absolutely will. So here we'll end up with the final product with the halogen on a completely different atom from where our oxygen used to be. So as you can see, we keep coming back to the same substitution and elimination reactions over and over again, and as we cruise through the chemistry of functional groups, we are going to see that even more. There is a reason why we cover substitution and elimination reactions early in the course, or at least most instructors do, as this is one of those topics that will just keep on resurfacing throughout the course over and over again. So to recap, ethers can cleave with HX acids via either SN1 or SN2 mechanisms. Primary ether cleaves via the SN2 mechanism, while secondary and tertiary ethers cleave via the SN1 mechanism. If you have a secondary ether, be aware of possible carbocation rearrangements, and if you have a phenyl ether, leave it with the OH group instead of the halide for the final product. If you learned something new today, please give this video a thumbs up, share and subscribe to the channel for daily organic chemistry updates. Leave me your feedback and questions in the comments below. I read all comments and I love hearing from you guys. This also helps to promote the channel so more students can see these tutorials. Thank you for watching till the very end. I especially want to thank Organic Chemistry Tutor members for your support and encouragement. Watch this video next to learn more awesome organic chemistry stuff, and I will see you tomorrow.